We will be talking today about image classification, basically continuing our discussion on the topic of image classification from last lecture. And we'll get a little bit into some topics that gets us closer to neural networks and ultimately convolutional neural networks and so on. We'll start with linear classifiers. Moving to the next slide. This was the syllabus that we've talked about last lecture, in the previous lecture, where we did talk about three major categories of topics: deep learning basics, perceiving and understanding the visual world, reconstructing and interacting with the visual world as the three major topics, and some sub topics that we will be covering in the class. And at the end, we will have some discussions around the human-centered AI aspects. And today, the goal is to cover the first three items: data-driven approaches. I will try to tell you what this means, and linear classification, as well as the k-nearest neighbor algorithm. So, like the previous lecture, let's start with our core task of image classification. Again, it's a core task in computer vision, and we actually come back to this task quite often throughout the quarter because it's a very good benchmark, and we have some examples to tell you how the algorithms work. So this is one of the items that we come back to quite often. We want to define the image classification task today, and then introduce two of the data-driven approaches for image classification. One of them nearest neighbor, and the other one a linear classifier. There are some other approaches which we have listed in our backup slides, and you're welcome to look at them after the class. But this is what we will be covering. So what is image classification? Given an image and a number of predetermined labels, a set of possible labels, such as in this example you see dog, cat, truck, plane, and so on. The job of the system is to assign one of those labels to this image. So to us, this is actually a very, very easy task because our brains, our cognitive system, is wired to get a holistic understanding of this image and assign a label to it. But when it comes to coding this and looking at how a computer can make sense of this image, that's completely a different story. And we want to see how machines can make sense of such data. So images are often defined by matrices of data. More broadly, more generally, tensors of data. And often the numbers are, each of the pixel values are between 0 and 255, which is an 8-bit data structure. And since this is an image, a colored image, assuming that it's with a resolution of 800 by 600, since it's an RGB image, it has three channels of red, green, and blue, RGB, and therefore it's a tensor of 800 by 600 by 3, as you can see on the slide. So, as you can probably guess, this is the semantic gap between our perception of this image and how the machine perceives and sees the image, right? And in order to be able to even understand how this could be very challenging. Let's look at some challenges, some variations in this type of imaging data. So let's assume, for example, as one example, let's assume that we move the camera. If the camera is moved, for example, panning the camera around, even if the cat sits completely and perfectly still, all of those pixel values, every single pixel value of 800 by 600 by 3 will be changed. So all these pixels will have a new value. Again, for us humans, it's the same object. There's absolutely no difference. But from a computer's perspective, it's completely a new data point. So this is one of the challenges, but there are quite a few others as well. For example, illumination is another challenge. So if you've seen or if you've taken courses in graphics or maybe other vision courses or digital image processing courses for engineering applications, you know that the value of each RGB pixel, the RGB values, are a function of the surface material, color, and their light source. And that's why same cat, same object may look differently in terms of numbers when it comes to being pictured in different illumination conditions. With that in mind, so whether the cat is in a dark room or under the sun, still it's the cat. It's one cat, but this is creating challenges for the machine. Can you maybe name some other challenges that may change the values of the pixels and create problems for the machine to recognize objects, other than illumination and viewpoint changes that I mentioned? So background clutter, background objects, yes. Which is actually our next slide. Yes, background clutter is another challenge. Anything else? Zooming in and out, yes. So scale basically of the object in the image. Yes. What else? The resolution of the image that could be considered as that's definitely a challenge, but often with machine learning models or any model that we want to recognize objects in images, since we normalize the size of the image, resolution may not be that important unless there is zooming effects of the objects. Occlusion is one of the major problems. Again, as humans, it's very easy to say, this is cat, these are cats. Even the last one, which is actually a very challenging, the one on the right, you can only see a tail and a little bit of probably paw in the right side. One could say, yes, that could be a tiger, or it could be, a raccoon with a tiny tail. But because of the context, because we know this is inside a living room on a couch, most probably it's a cat. So again, for us humans, it's not that hard. Beyond that, there are many other problems. Deformation. Cats are very deformable. So they create challenges for algorithms to be detected, recognized. I mean, not today's algorithms, generally for building step-by-step algorithms that can detect objects. So deformation is one of the other major challenges. And beyond that, the intra-class variation is one more important challenge. We know that cats can come in different sizes, colors, patterns, or even they have different breeds, and all of those are still cats. But for the machines, it's not that easy to recognize the intra-class variations. One other interesting challenge is the context, because if you only look at that part, that image on the right, or if an algorithm looks at this without considering the context, it's very easy to classify this as a tiger or some other animal. But because of the context, and because we know there's the effect of shadows and so on, this could probably be classified correctly. So, but the thing is that the classifiers that we have today can do really great good jobs at classifying the images, identifying the objects in images, thanks to efforts like ImageNet and also all of the follow-up works that created larger scale benchmarks for training larger scale models. And in this class, what we want to do is to get to a place that we build models that can recognize objects and also other aspects within the image. For the rest of this class, we are going to be working towards building step by step the building blocks that are needed for building those large algorithms. And before doing so, we have to look at the most basic building block of classifying an image, and that is implementing a function like this. So if you've taken some of the computer science or engineering courses that often build frameworks through algorithms, like for example, sorting as a computer algorithm, it often comes with some if-then-else rules and some for loops and so on. So there's a clear flowchart of tasks and steps, if-then-else steps that creates an algorithm for sorting. But when it comes to images and understanding the visual world, that is not happening. That is a challenge. There is no way to hard code the steps for classifying images. Although there has been some efforts in this space. There are papers that they've tried to come up with algorithms and steps to recognize objects, and one of those was based on edge detectors, finding the edges in the image as a first step, and then after creating all of these patterns, look at the important patterns, for example, corners, extract some features that are around the corners, or count the number of specific types of corners, and based on those, from those, try to map that into the output class. So while this has been an interesting effort and it had some success on very limited variability of type of images, but this is very hard to, first it's very hard to scale these types of algorithms. Even if it works, it's very hard to scale because you have to create these rules and everything for every single object that you want to recognize. And second, finding the logic for each of those requires a lot of effort by itself as well. So because of these challenges, I think these types of algorithms, which are based on creating logics and procedures for detecting objects or classifying images, have not been quite successful. And machine learning comes with this data-driven approach. So with this new paradigm of, and another paradigm of looking at this problem from a data-driven perspective, we define a procedure of a three-step process. And the first one is to collect data sets of images and their labels. So there are many different ways of, so if you want to recognize a specific type of object, or specific types of objects, we can look for data sets or single data points over the internet to create a data, many samples from each of the examples. We used to be doing this 10, 20 years ago using search engines and image search engines over the internet to create these types of data sets. Now we have all of the data sets. So, and then the second step is using machine learning algorithms to train a classifier. Basically, build a function, train, that takes the images in the training data and their associated labels and builds a model that can associate images with the labels. And then the last step would be evaluating the classifier on new images, which means implementing a function called predict that takes the model and some test images, and for those test images that were not part of the training images, predicts the labels and returns those as the output. So a very simple procedure, but instead of building a logic, we are building a data-driven approach for it. As I said, we want to talk about two popular methods and classifiers. One of them is nearest neighbor classifier. This is the easiest form of classification, and we specifically want to go over this because we can learn some of the concepts around building these classifiers, and it's easier to explain some of the details, and then we'll move to the topic of linear classification. Okay, to do that, what we do to build the nearest neighbor classifier, as I said, we need to build the train and predict functions. The train function needs to just memorize all of the data and labels. So the training function basically doesn't do anything other than keeping everything in the memory. And then the prediction function, the predict function, looks for the most similar training image. Basically, it creates a lookup table of all of the images and all of their labels. And during the prediction or testing time, what it does is tries to find the closest one, the most similar image, and output the label for that image. Let's look at an example. So assuming that we have these 5 as in our training data, then yes, you see my cursor, and then this is the query image, the input image for prediction. What we want to do is to see which of these training data and training images is the most similar to this one. And for that, we need a distance function. So this distance function needs to take the 2 images, each pair of images, each of these images compared to the query image, and return a value which defines the similarity between these 2 inputs, these 2 images. There are many different ways of doing that. One of the most popular ones is L1 distance, which is defined as the sum over all absolute values of pixel differences between the 2 images, image I1 and I2. As an example, if this is a testing image, if we want to calculate the distance of this image with an image in the training data, we do a pixel-wise subtraction and the difference between the pixel values, and then sum them up, which defines this value as the distance between these 2 images. So this is the most basic distance function, but it's actually very useful in many applications. We'll be coming back to this L1 and other variations of distances in the class quite often. With this very simple definition, we want to see how we can get this implemented. As I said, the first step is to just memorize the training data. So the train function just keeps the data in the memory, and then what the predict function does, using actually some Python libraries and NumPy and so on, we can implement this in just 4 lines. We calculate the distances between each of the testing samples and the training data, take the minimum for each of the testing samples, and then output the label for the one with mean index. So this is going to be the implementation for the predict function. Yeah, the pixel values, as I explained, the simplest form. This is a tensor of 800 by 600 by 3, and 3 channels, and these are RGB values for each of the pixel locations. So yes, I should actually repeat the questions for online students too. And the question was the pixel values, what do they represent? Yeah, so the next question is why it's between 0 and 255. So there are many different standards for storing images. The most popular one that we use in almost all images that you see online and here they are RGB. RGB is a 24-bit format, sometimes 32 because there's another channel alpha. We don't want to get into those, but the 24-bit format, it means that for each of the channels, for each of the 3 channels of red, green, and blue, which create all color combinations, we can have 8 bits. So that's the standard that is defined. There are some other frameworks too, but this is the most popular one. So with that, let me go back to the code and ask you a question. So I know some of the students, most of the students come with engineering backgrounds and a little bit of computer science as well. But we want to see with, say, N examples that we have in the training data, how fast the training and prediction happens. I'm hoping that you're familiar with the big O notation that we often represent computational and sometimes space complexities with. But here, if you look at the algorithms, I'll go with the training data. In the training function, and then I want you to help me with the answer for prediction. For the training step, the training is of O1 because we are not actually doing anything. We are not even moving any data. We're just keeping the copy of the data in the memory. So no operations. It means that without operations, with operations of order 1, we can complete the training step. What about the prediction step? For each of the single examples of the testing data, how many operations should we take? N. Yes, if we have N training data, it means that we have to calculate the distance of every single testing image with all of the images in the training data. So at least in the order of N operations. So this is not really good, because what we often want to do is, because training is not doing anything, but during testing, during prediction time, we are spending so much time just to do comparisons between the data and each single data point and the training examples. This would be similar to the fact that each single time that you ask ChatGPT a question, it will try to see what the answer is and compare it with all of the possible answers over the internet, which will take years, and then return your response, right? So it wouldn't work when it wants to scale. For very simple problems, we used to be using these types of approaches. So what we often want is to build classifiers that are fast during prediction. They do it much faster, but it's okay if they take a lot of time to do during the training, because that could be done offline. So with that in mind, although there has been a lot of efforts making nearest neighbor much faster using GPUs and so on, which are beyond the scope of this class. If you're interested, you can take a look at those. But with that, I want to look at some of the visualizations and how this algorithm in general works. So given this space that we have 5 classes of red, blue, green, purple, and yellow, and each dot represents one training sample in that class. If we partition the space for every single point, you see that we can create these 5 partitions, let's say 5, or in this case 6 different partitions, that each point, if we have a testing sample that is in that specific region, the color of that region shows what the nearest neighbor for that sample will be. So this is going to be the nearest neighbor algorithm, one nearest neighbor algorithm, partition the space in this setting. But do you see a problem here in this example? So the yellow one is in the middle of all of the greens, and this means that probably that's an outlier. That's probably a noise, and this is the case for many, many problems that we have to solve. And with that, the reason that there is this big yellow region in the middle is just this single point, and because we are only using one nearest neighbor, this happens. So to make it a little bit more robust, we can increase the number of nearest neighbors that we take, which turns the nearest neighbor algorithm into a k-nearest neighbor. And we often select more than one point or sample, and we often take the majority voting for identifying the label for any given testing sample, testing image. But the problem that you can see here is now we have some white regions. Those white regions are areas that we cannot make a decision, a complete decision, because those areas are areas that we have equal number of samples from the neighbors, from the 3 different classes. And there's no way to identify what the label of that example in the white region is. And for you, if you create these types of spaces for your problems, this means that if you look at these spaces, it means that those are good regions to go and collect more data for. So those are unclear spaces. So it's a good way of finding regions that are important for data, more data collection. Okay, so we can go larger on the value of the k, but one of the choices that we have, one of the factors that plays an important role is the value of k. But if you remember, we had another decision to make, which was the distance function. We talked about the L1 distance, again, sum of all of the absolute values between pairwise differences of the pixels. And if I visualize the L1 distance, or sometimes in some contexts we call it Manhattan distance, the distance function is kind of visualized in this way. If I calculate, if I look at this square that I have in the in this space, all of the points on that square they have a same distance from the origin, from the center point. So this is a good way of visualizing and seeing how this L1 distance function works. Another popular framework, another popular distance function that we use is L2, which instead of the absolute value, calculates the square of the differences, sums it up, but because of the square, we also do a square root. And visualizing that, we'll get this circle visualization where each of the points on the circle they have the same distance from the center, from the origin. So this visualization actually helps us understand the differences between these distances too, and these are the most basic and easiest distance functions that we can use. So there are, again, a lot more. The reason this visualization is helpful is because sometimes if you rotate so x and y in these two visualizations are basically the features. If we have 2 pixel values, two features, then we have this 2D space, and this x and y are often those features. So if I rotate these features, meaning if I use other types of features, this L1 will have a different framework, different value, while it's not any different for L2. So that's why this is a big difference between L1 and L2. And sometimes if our features are very specific and meaningful and we want to preserve their information, often L1 is more important, is better, because it has kind of, as you can see, a shape that preserves and enforces distances based on the features. But if features are more arbitrary, then L2 distance makes more sense. If I want to calculate the distance, so the distance of all of the points on this shape from the origin are exactly the same, right? If I use the L1 distance. But for L2 distance, the points on this circle have the same distance from the center or the origin of this space. So that's basically the main, what these two images are showing. Any point on this shape, when using an L1 distance, have the same distance from the origin. And for the circle, any point on the circle, if you're using L2 distance, you'll have the same distance from the origin. Yeah, why it's important is better to use L1 if we want to preserve the features. So to answer that question, if I rotate the feature axis, the distances and this distance function changes completely, right? While if I do the same here, nothing changes. It's the exact same value of the features, right? Distance, sorry. So in this case, L1 is very sensitive on the feature values, while L2 is not. If you select another feature in the same space that is having a different, creates a different shape, then your L function, the distance function changes as well. So if I draw the lines here, again, the question for online students is why it changes if we rotate. If I select another feature that goes from this side, right, then the lines will look different, right? So if you rotate this thing, but for that shape, it's agnostic, right? So with these two distance functions that we talked about, if I revisualize the space, you can see with k equals to 1, with one nearest neighbor, with L1 and L2, these are the space partitionings. One of the interesting things that you can see here is that with L1 function, most of the boundaries are parallel to the two axes, the two features, x1 and x2, very much sensitive to the features, while there we have a little bit of more smooth boundary separation. So there is a tool online on the lab website that you can play around with this, with different distance functions and different number of k. You can create a different setup, so you can play around with it. But why did we talk about nearest neighbor to begin with? First, yes, it's the easiest problem to solve, easiest solution, easiest data-driven approach, and great to start with. But one of the main reasons that we want to iterate and discuss nearest neighbor is the fact that we can look into the topic of hyperparameters. Hyperparameters are often some of the variables that you have to make a decision on to be able to run your algorithm. In this case, the value k, the number of nearest neighbors, is defined is a hyperparameter. Depending on how many number of nearest neighbors you take, your outputs will be different. And then another choice that we have here is the distance function. So the choice of hyperparameters are often very much dataset dependent and sometimes problem dependent. And we have to have a way to identify those, to kind of optimize for them.